Debugging an AI system usually means repairing a structure that already exists. But building a net new agentic use case requires constructing the logic from zero. Take a concrete test case: building an automated agent to manage retail staff schedules. The task is to assign 8 employees across a completely blank weekly calendar. The schedule has absolute boundaries, employees have specific availability windows, and there are strict limits on the number of shifts anyone can work. Because these rules are rigid, we can evaluate the AI's output programmatically. A simple Python script reads the final schedule and counts the exact number of rule violations. There is no room for subjective interpretation. A schedule is either perfectly compliant or it fails. This strict binary gives us an exact sandbox to test the limits of what an AI agent can handle. To solve this, an engineer has exactly 3 variables to adjust: the underlying model, the API harness, and the prompt itself. Pushing any of these 3 levers in the wrong direction forces an immediate trade-off. You will pay for a mistake in higher operating costs, slower latency, or degraded accuracy. We can map these thresholds by applying a chronological hill climb. We test combinations of these levers, observe exactly when and how the system breaks, and iterate until we find a stable configuration. Identifying exactly where these limits lie is the difference between an experimental demo and a reliable production system. We start with a baseline attempt. Deploying a lightweight model, Claude 3.5 Sonnet, with a basic JSON output prompt yields a complete failure across all 5 test cases. The system cannot resolve the logic. To map our next steps, this 3D scatter plot will track our progress. It graphs the model's accuracy on the vertical axis against the cost and latency required to generate a response. Keeping the prompt identical, we scale the model lever up to Opus 4.7. The larger model reduces the sheer number of scheduling errors, but it still fails to pass the 5 absolute test cases. We get a slight lift in accuracy, but at a higher operating cost. For the 3rd attempt, we adjust the API harness. We enable adaptive thinking, allowing Opus 4.7 to determine its own reasoning time before answering. The result is perfect compliance. The accuracy metric hits the ceiling, but the cost of that perfection is significant. The latency spikes to 100 seconds per response, and token consumption triples. The perfect accuracy data point is pushed entirely off the viable bounds of the chart. In a real-world deployment, a system that takes nearly 2 minutes to generate an answer is just as broken as a system that confidently hallucinates. To fix the latency, we retreat to the faster Sonnet model, but this time we pull the prompt lever, drastically expand the instructions, forcing the model to explicitly reason out its math and check its work. The expanded reasoning helps. The model successfully passes 2 out of the 5 test cases. However, in the remaining 3 cases, it fails for a structural reason. The math requires so much scratchpad space that the model hits its maximum output token limit before it can actually finish generating the schedule. You could technically raise that maximum token limit in the API, but doing so instantly drags the system back into the severe latency delays of the 3rd attempt. Relying on a single monolithic API call to simultaneously draft a schedule, evaluate its own logic, and edit the final output inevitably hits a physical bottleneck. The solution is to abandon the monolithic call entirely and distribute the work across an agentic microsystem. This flowchart illustrates a generate, evaluate, repair loop across 3 processing nodes. Step 1, the generator, creates a rapid first draft. The draft feeds into the evaluator, which locates rule violations. Finally, the repair prompt applies surgical fixes to those errors, locking in a final schedule. This loop passes 100% of the test cases. Because each step is tightly constrained, it consumes fewer tokens and operates with much lower latency than brute forcing the problem. Distributing the logic into specialized microagents resolves the accuracy and latency bottlenecks of the single prompt approach. Beyond speed and cost, this loop architecture accommodates new constraints that emerge at runtime. Consider soft constraints that arise mid-week, an unexpected need for a Wednesday shift, or a sudden interpersonal conflict where 2 specific employees can no longer be scheduled together. A dynamic loop allows the system to adjust at runtime. The individual shift elements instantly reorganize themselves around the newly introduced relationship variables. Because the evaluator node is a language model, an engineer can inject these soft constraints on the fly using plain text. There is no need to rewrite the rigid backend Python validation logic. Production-ready AI engineering favors the design of the architectural workflow over the size of the individual prompt.